Looks good. Go ahead.
Okay, good. So my name is Thomas Steinke. I'm heading the supercomputer department at the Zuse Institute, and I want to give you an update what's going on at our site. For those of you which are not much familiar what HLN4 means and what LISA means and how does this comes together, an update here. Oops. So HLN is a special construct in Germany. So we are at the tier 2 level. That means we are not at the top of the supercomputer centers like Leibniz Computer Center in Munich or in Jülich or Stuttgart. We are on the next level below. And as you may know, there's a gap in the funding and in the economy between the northern and southern states of Germany. So the more poor states of Germany came together around 2000 and thought what we can do to support HPC users in our local states. And so the HLN, which is the Northern German HPC Alliance, was formed, and since then we are in operation. HLN has two sites for different reasons. So one site was always at our institute, the Zuse Institute, and another site in the state Lower Saxonia, and it is currently the University of Göttingen. Before it was the University of Hanover. And so all the 7 states bring their money together and fund the investment and operating costs of the system. We are now have the 4th generation of system, and how it looks like I will tell you here. So this is LISA. LISA is a system at our site, and there is a sister system at the University of Göttingen. And the numbers I put here on the slide are the numbers of our system. So we got the final configuration of our LISA system in April. That means basically we had the major system up and running in December last year, but we could upgrade with another set of nodes to now 1217 nodes. All nodes are dual socket Cascade Lake AP nodes. So that means we have 96 Xeon cores per node, which sums up then to more than 120K cores in the full system. So the over system is a little bit more, consumes a little bit more, over 1.3 megawatts. That is one limitation at our side. We can go maybe up to 1.8, maybe up to 2 megawatts. But this is then the ultimate limit because in our data center we house other clusters and resources for internal use at the Zuse Institute and for partners. So with these numbers above, you can calculate a peak performance of about 8 petaflops, and with the HPL, we are on the position 48 in the top 500 from last June. We will probably go down over the next years as usual in that business. This system is actually the first system at our site where we can have a cooling system with warm water. So we did some reconstruction of the infrastructure to support warm cooling. We would be happy to have even warmer water for cooling, but this is currently limited for technical reasons. So our inlet temperature is about 30 degrees Celsius. Theoretically, our in-house infrastructure would support up to 45 or maybe even 50 degrees Celsius, but this is as it is now. So if you want to know what we can do with the system, here are some key numbers. In orange, the numbers for the overall HLN4 system, which includes our sister system in Göttingen. So peak performance is, as I mentioned, 8 or 16 megaflops. That is 5x improvement over the previous generation, and our selected benchmark set gives 3.5x over the previous system, which was a Cray XC40 system. And we could double the space for the online storage to 8 and 16 petabytes respectively. So the user community is a very broad one, as we have to support all the science which happens in Northern Germany and beyond. So we have a few users from Germany, Europe, and even from other countries in the world. In total, we have today roughly 300,000 users on the system, and we have to support what we call large projects, that are those projects which has to be reviewed by an external science body. We have 200 of these large projects to support, and as you can imagine, this is from a broad range of physics, chemistry, engineering, earth science, and life science, and of course, as probably many of the HP systems nowadays on our system as well, we have simulations related to the COVID-19 pandemic. In particular, on our side, there are agent-based modeling for predict the behavior of the spread out depending on the nature of how the contacts are, which policies at schools, and so on. For different geographical areas, for Germany, or for Berlin, or for regions in Lower Saxonia, for example. And the idea is to make foundations for the politics for decisions. So that's the hardware we had in April, which is running on production. What we have now is our new baby, which is currently in the installation phase, and this is the Intel distributed asynchronous object store. So we are looking further to dive into an alternative for Lustre. So we will build up in DAO's IO testbed, which will have a total capacity of half a terabyte implemented in SSDs, and then 30 terabyte in the Optane data center persistent memory. And the expected performance we hopefully see soon will give us 2x in the bandwidth, but more importantly, as we have a Lustre system without a burst buffer currently, we can better support workloads which require large IOPS rate. On the bottom, you see the configuration. That might be not important now. So you may question why we choose DAOs. And as I mentioned, it turned out the vendor we chosen was not very keen to give us a burst buffer, although we had a benchmark supporting burst buffer or in general a higher IOPS rate. So we have currently a system which is not good in that. There might be other either complementing or alternative solutions to Lustre. Of course, the simplest one would be add a burst buffer into the Lustre systems, but that was not way we decided not to go for various reasons. There might be BGFS, in particular with the Beyond option, where you can aggregate local SSDs over multiple nodes to form a file system on demand for a given job. And there's DAOs, and we are watching the DAOs development over the last 1.5 years or so, and we go for that for various reasons. One is, for instance, to support better today's simulations, which have a mixed I/O pattern. Mixed means here that's a combination of streaming, where Lustre is not bad, but also require high IOPS rates. And this we see, for instance, for some CFD workloads where IOs happen on many small files, and in a very short time there's an IO burst. We also want to support the raising portion of AI on DL workflows, and for that we are very much looking forward to collaborate with the scientists to support them on our system. And with that, I close my presentation. Thank you.